ماشي.
So this course, there are very nice books. I think I already gave you this topic of these books. One of the book is Rocket Propulsion Element by Sudan, and another is Fundamental of Rocket Propulsion by D.P. Mishra from IIT Kanpur. So you can refer those books in addition what we are learning in the class. So this already we tried to see last time how we can classify rocket propulsion. It is classified in number of ways. By some of these are according to energy type, by their constructional feature, by the type of the vehicle they propel, again by the size, by the type of propellant, by the type of construction, again by the number of rocket propulsion units, and by the method of producing thrust. So this is the way how we can classify rockets. So this is simple constructional feature of a particular rocket. You can see nozzle here. Okay, here you can see the nozzle, and nozzle consists a number of things or number of constructional features. Again, there are some stages. For example, this is about two-stage rocket or three-stage rocket like. So one stage is here, another stage is here, and payload or other important items that we are sending to space are here. So these things are very sophisticated parts of the parts of rocket which we are sending to space or somewhere else. We don't know. So these are called payload or so there are some igniters, there are some internal insulations, and there are solid HTPBs, hydroxyl terminated polybutadiene propellants. There are some other, many components are there. So I don't know, one day we may go to Ambo and you can see this rocket in, you can visit it. It is there. This is available in Ambo. Okay. Actually, I went yesterday to Ambo with our students, but I planned to take you there, but I couldn't because of some constraints. Okay. So this is some constructional feature. So 88% of the total mass is considered as propellant, not even more than 88. Only 12% of the construction of this thing is of the important unit of the rocket. The remainings are almost propellant because the major part of rocket is it is propellant only in order to arrive the given vehicle into the required destination, so that we need more propellant than the structure itself. So structural units are there. The payload or the important item that we are taking into space is take a very small size, means mass. Okay, so there are some detaching mass, that demi mass will be detached and thrown to and then we can accelerate our vehicle forward after detaching those things. That is called the stage separation. Okay. Working principle of rocket motor. We have rocket motors and rocket engines. The name rocket motor is for the solid propellant case, and the rocket engine is for liquid propellant case. We are not calling them as rocket motor or simply rocket engine. So if it is liquid, we call rocket engine, and if it is solid propellant case, we call rocket motor. So how we can construct the working principles already we discussed in last time, how we are it is working. We already learned it. So the change in velocity that we obtain from the rocket is related with this u is exit velocity ve. This u is ve, that is exit velocity. that the propellant is propelling through the convergent divergent nozzle. So this U related with VE. And M naught is the initial mass or the weight mass of the rocket. And then final mass is the mass of the rocket after some propellant is consumed. Okay, so this is the relation, that how we can get some amount of change in velocity from time to time. And whenever some amount of propellant is consumed, the acceleration or the change in velocity will take place. It means our rocket will accelerate in more appropriate manner. Means high acceleration will be obtained. So there is chemical energy from the chemical propellant in the combustion chamber, and that chemical energy is changed into thermal energy in the combustion chamber. And this high temperature gas will eject through the throat area of this rocket motor. This is a simple rocket motor. So it will come out and accelerate through the divergent nozzle. So as the ejected matter or the burnout mass is coming out at some speed, that is VE, and then that produces the thrust force. So that is related with the this component of force, that is the thrust component. Okay, so there are pressure component of force also. That pressure component of force is related with pressure at exit minus atmospheric pressure times area exit. So this is called pressure thrust, and this is called momentum thrust. So there are two components of thrust. Okay, so if atmospheric pressure and exit pressure is the same, then the pressure thrust component becomes zero, and that is known as optimum expansion of nozzle condition. And if there is pressure exit is greater than pressure atmosphere, then what we call over-expanded nozzle condition will come. And if it is less than, then under-expanded nozzle will come. So there are three conditions here: optimum expansion, over-expansion, and under-expansion of the nozzle. So this is a simple constructional feature of solid rocket motor, or simply rocket motor. So we have combustion chamber, we have nozzle section. In the nozzle section, you can see 3 points, 3 different regions. One is the convergent region. After the combustion chamber, you see it is narrowing it. So it is divergent section. And then it goes to very minimum cross-sectional area known as the throat. So after throat, you can see divergent section, so which is helping the acceleration or helping to accelerate or to move in high velocity. The ejected matter will go in high velocity through this area. So here there is low velocity, that is subsonic region in the divergent region. At the throat, it's considered as Mach 1. Mach 1 means transonic kind of flow. So after Mach 1 to this region or exit region, it is supersonic region. So it is divided into 3 different regions, and that the principle of momentum conservation works here. The principle of mass conservation works here. The principle of energy conservation works here. Okay. So this is classification of rocket propulsion. We already discussed in last time. Simply rocket propulsion, chemical propulsion, electrical. There is also nuclear propulsion, ion propulsion, thermal propulsion. Again, we have in chemical propulsion 3 categories: solid, liquid, and hybrid propulsion, based on the propellant we are using. If the propellant is solid, then it is solid propulsion. If the solid is liquid, it is liquid propulsion. And hybrid propulsion is the combination of the two, that liquid is there, solid part is there. And when we come to liquid propulsion, monopropellant propulsion is there, bipropellant is there. So mono means the constituent propellant having the same characteristics or one, but bi means two propellant characteristics. So based on that, we classify like this. Okay, so this is a simple summary of the working principle of the use of Newton laws. All Newton laws works here. Okay, all the Newton laws are applicable. So when we come to propulsion system type, cold gas propellant, monopropellant, biopropellant, solid propellant, this already we discussed last time, so I don't want to waste much time here. Okay, so this is the design consideration of cold gas propulsion system, advantage and the disadvantage of cold gas system. Again, monopropellant system, what does it mean? So this monopropellant system, another name is called hydrazine thrusters. So N2H2, H4 is the hydrazine, so which helps us to use monopropellant system. Okay. Another is bipropellant system. So in bipropellant system, we have two types of propellant. Oxygen is there, fuel is there in bipropellant system. Sorry. Hello? Hello? Abid? Javier Maska. Okay, Bahala double shelter. Okay, so in monopropellant, we have only one propellant, that is hydrazine. Okay, this is the chemical formula of hydrazine. And in bipropellant, we need two types of things. One is the oxidizer or oxidizing agent, and another is the fuel. So in this system, we need many types of pumps and connections or valves. So because of that, it is intricate kind of system, and it is very difficult. But managing or controlling the mechanism of burning in this system is easier than others. Okay, there are two types actually, two types of biopropellant system. One is gas generator, one which contains gas generator, and another one is simply having small valves. And so this is pressure feed system. We have pressure, high pressure gas are here, so it is called pressure feed system. And another one is pump feed system. So we have pumps on it. You see, there are pumps in between this valve and this valve. Pumps are there, turbines are there, gas generators are there. So this is called the pump feed system. And this one is having only pressure, high pressure gas in cylinder here. So it is gas feed system. Okay, so this is bipropellant system. So bipropellant contains oxidizer and fuel in separate tanks, and which are connected with some feeding systems. And then this will come to the thrust chamber. This is called thrust chamber. There is combustion chamber here. There is throat here. There is exit here. So it is completely known as thrust chamber or combustion chamber, or simply we call motor. Okay. Okay, so let's come to the solid motor system. So in solid motor system, we have various components. One is the casing, another is propellant itself, nozzle is there. So this is called there is also igniters, there is also the protection, what they call, protection layers. We can see them here. It is insulation is there. Insulation means high energy or the high temperature that created inside the combustion chamber will not come out to the structure. So to protect the structure from heat, we have to place an appropriate type of insulation. So insulation is there. Okay, there is propellant is there, igniter, solid propellant igniter. We can fix it at some appropriate position. The nozzle design is here, means convergent, divergent, and throat condition. So this is a complete assembly of solid rocket motor. So you are expected to design at least this motor. From this time onward, just consider how to design this motor. What is the cylindrical casing? What is the size of the dimension? What material? From which material it is manufactured from? What is an appropriate insulation material is required? And what type of igniter types? We have pyrogen igniter or we have pyrotechnic igniters. And how we can design the nozzle itself. Nozzle design is very critical issue. So you must consider how to design. Just search many books on this and try to design nozzle from this time onward. Try to design, first select an appropriate propellant. Means we have solid propellant of this shape, cylindrical shape with internal perforation. So there is cylindrical hollow internal surface is there, or it can be star shape, or it can be depending upon our requirement. If we need some progressive burning, if we need regressive burning or neutral burning, based on our requirement, we can select one of the type of propellant. And then after selecting propellant, we have to design igniter for that particular propellant. Then after, we have to consider the heat shielding material. That means the insulation material. And then the motor casing or cylindrical casing will be come out. That cylindrical casing is designed based on the aerodynamic principle with no external extrusion or some extra parts. So it should be a smooth cylinder with an appropriate strength in order to overcome the aerodynamic loads and other loads. Okay, so this is what you are expected to design in this course. እየሰማችሁኝ ነው አይደለ? ሄሎ ሄሎ።
አዎ እየሰማኝ።
ስለዚህ ከዚህ ቀን ጀምራችሁ እነዚህ ኮምፖነንቶቹን እንዴት ዲዛይን ማድረግ እንዳለባችሁ ብቻ ሳይሆን ዲዛይን ማድረግ ጀምሩ። ይሄ እንደ አሳይመንት ልስጣችሁ። ኖዝል ዲዛይን፣ ሰሌክት ፕሮፔላንት ሰሌክት የምናደርግባቸው ክራይቴሪያ እናያለን። ፕሮፔላንት ሰሌክት ከተደረገ በኋላ ምን ይመጣል? የፕሮፔላንት ኢግኒሽን ሲስተም ዲዛይን ይመጣል። ዘን አፍተር ዘ ሪሜኒንግ ሌሎቹ በዛ ተንተርሰን የምናመጣው ነው። ኮምበስትን ቻምበር ፍሪ ቮሊዩም የሚባል ነገር አለ። እነዛን ታስታውሱና ከዛ በኋላ ኖዝል ለዚህ የሚሆን አፕሮፕሪየት ኖዝል ዲዛይን። Okay, then after the external shell or metallic structure of the which covers overall engine will be come out. So then at that moment you have to consider which type of insulation is appropriate for this type of ይሄን እንትን በሉና ካሁኑ ጀምሮ የምትሰሩት ይሆናል ማለት ነው። እንደ አሳይመንት ነው። So actually we tried to compare this cold gas, solid motor, monopropellant, bipropellant by their behavior. We already checked them or discussed on each of these things. Okay, so chemical propulsion system, one is solid propellant, solid propulsion rocket, liquid propellant rocket, hybrid. So this is solid one, this is liquid one, and this is simply the combination of the two. Okay, so it contains oxidizer tanker from the liquid, it contains fuel grain from the solid. So solid fuel and liquid oxidizer gives us hybrid propellant rocket. Okay, so these are, okay, yeah, this is just solid propellant rocket. So how it works. Less. In solid rocket motor, the ingredients to be burned are already stored within the combustion chamber. So this is the solid propellant. The solid propellant or the charge is called grain. We call the solid propellant because it is manufactured from different type of grains, chemical grains. So, and it contains all the chemical elements for complete burning. Okay, complete burning means there is no residue expected to left. Whenever it burns, it has to be burned completely. No residue material left. Once ignited, so once the ignition signal is given, this ignition system by itself needs a careful study. Okay, it can be a topic of somebody of you for your master thesis. Ignition system alone is a topic. So once a proper ignition will be ignition energy released from the igniter, then this the igniter energy will transfer into the exposed surface of the solid propellant here, the exposed surface. So this exposed surface immediately caught by fire or high energy, then it start to burn internally. So once ignited, it is designed to burn smoothly at a predetermined rate. There is known as the rate is known as burn rate. There is a burn rate calculation we can see later. So we have to provide an appropriate burn rate for this type of propellant on all the exposed internal surface, grain surface. Then initial burning take place at internal surface of the cylinder perforation. Perforation means the hollow section. And the slots maybe are there, some kind of slots, star types or other various configurations is there. So the resulting hot gas flows through supersonic nozzle to impart thrust. Okay, so that is the method what we are moving our vehicle forward. Once ignited, motor combustion is designed to proceed in an orderly manner until all the propellant has been consumed. So our aim is to burn the given propellant consumed properly. So this is constructional feature of solid rocket motor. Okay, this is igniter here. Thrust terminator is there. There are insulator, internal insulations are there. Motor case or the outer casing or the cylindrical metallic body. There are thrust vector control mechanisms here. Nozzle throat is here. Okay, propellant grain is here. Okay, so it contains these all components. Okay, so this is a constructional feature of solid propellant rocket. So solid rocket motor case is one of the components. So we are see this structural components one by one here. Okay, motor case we give motor case RMC. RMC means rocket motor casing or case. Means the outer cylindrical shell. Maybe it can be steel, it can be aluminum, or it can be other material based on the amount of external pressure or the amount of aerodynamic loading that that can affect the shape. If we expect much external aerodynamic forces, then we use stronger material. But in most cases, aluminum tube is used because of the lightweightness of the material. Because rocket in rocket design, the lightweightness is one of important parameters. Okay, so in rocket motor, generally consists of steel or aluminum tube with its head in the dooms. There are a doom. You can see this is the doom. You see here, this is doom. This is external casing. Okay, so dooms are there. And aft end dome houses or supports the nozzle. So here, this dome, head end dome and aft end dome. You see, this dome supports the nozzle not to come out because of the high thrust force or the high speed ejection of burned propellant mass. So this is aft dome, forward dome. Here also you can see there are some dooms here. This is also doom here, front doom. Okay, so this should be under consideration. Okay, RMC have insulation on its interior surface for protection against the thermal failure. And this, which is made for high strength steel, from high strength steel, or by filament winding. If we are using composite material, then it should be filament winded composite. This structural component, because high strength steel is highly denser, so the density of steel is high. Our requirement is to have less density material, means that less density contributes to the weight. Okay, so because of that, sometimes we use composite which is made from filament winding. Okay, so composite which is made from high strength fiber on suitable form of resin material, because composites are made from fiber and matrix material. So on an appropriate matrix, we have to use filament winding in order to get low density material. In motor cases, the front and aft dooms are wounded as integral part of the case. So when we are manufacturing it, the front doom and the aft end should be an integral part of the casing, with suitable opening and fixtures includes to permit the removal of the motor case and loading of propellant and attachment of igniter and nozzle. So those aft end and front ends are kind of integral parts. Okay, so you can come. Sorry, nah. lumata ya. Sorry, so it is an integral part of the casing. Okay, so the motor case consists main structural components of the rocket and must be designed accordingly. Another important component is solid propellant. So this solid propellant is a solid cast material. It is made by casting. So the chemical ingredients are cast together, and it contains fuel and oxidizer in proportion, an appropriate proportion. Okay, and which are bounded in suspension that can produce thrust through the chemical reaction. So the fuel can be handled at room temperature until ignition sources are applied. That means that ignition may be at some required condition. When the propellants are ignited, they release both fuel and oxidizer constituents, which burn and generate the required thrust. So this is an igniter which is placed in the front dome in order to facilitate some burning. And then this is the propellant. Okay, so this, once ignition is started, the propellant internal surface is caught by high energy, source, and then it starts to produce high energy or high velocity eject matter. So this is the eject matter coming through the nozzle. So this is a simple nozzle construction. Okay, so burning surface from the inner. Again, burn propellants are coming out like this, and engine casing is mounted. This is a metallic engine mounting. Okay, and heat resistance material, especially on the nozzle, at the point where high erosive burning will or high pressure will happen at the point of nozzle. So on that particular point, we must provide not only on that part, but on the portion where high velocity mass of propellant coming out. So those parts are prepared or designed with heat resistance material. So we have to select heat resistance material for nozzle design, because there is erosive burning take place. So that produce it will wear out the material will immediately damage if it is soft material. The material selection is, for propellant is an important parameter. So propellant for solid rocket motor are made from wide variety of substances selected for low cost. Cost aspect must be under consideration, safety aspect, and performance. So it integrates all the cost, safety, and the performance. So we can select materials or propellant material based on these parameters. So the selection is strongly affected by a specific application. Typical ingredients are, for example, ammonium perchlorate is one of the granular oxidizer. Ammonium perchlorate is oxidizer, and powdered aluminum is a fuel. So this ammonium perchlorate is combined with powdered aluminum, then we can get another one type of propellant. And hydroxyl terminated polybutadiene is used as fuel that is liquid during mixing and polymerization. So this HTPB is for the purpose of polymerizations, to make it rubbery binder during curing. So this is called curing agent, or at the same polymerization agent. Higher performance is achieved by use of energetic oxidizers. For example, cyclotetramethylene tetranitramine, we call in short HMX. So this if HMX is one of the part of our oxidizing agent, then we can obtain high performance propellants. Okay, there are some energetic fuel like plasticizers or binders. Okay, which are nitrocellulose and nitroglycerin. Nitrocellulose, nitroglycerin these are double base propellant types. Nitrocellulose is a single base propellant alone, but nitrocellulose with nitroglycerin combination, which gives us double base propellant. Okay, we call this them in short DBP, double base propellant. Among different form of chemical explosives, we have TNT also, that 2,4,6 trinitrotoluene. That is one of the high performance propellant. Again, hydro 135, the chemical name, which is called RDX. This RDX is another name, research and development explosive. Okay, so which is one of among these high performance propellants. So HMX, RDX, TNT, these are high energy or high performance propellants, which are used as energetic oxidizers. So powdered aluminum is still used as a fuel. And the propellants mixtures containing nitrocellulose and nitroglycerin have a detonation velocity of 7.7 kilometer per second as explosive. These are explosive propellants. Okay? And their their ingredient is known as devil base powder or devil base propellant type, because nitroglycerin is one of the strong type of monopropellant. Nitrocellulose also another strong propellant. So that the combination of the two gives us such kind of detonation velocity. This is high detonation velocity. Actually, this is the velocity required to maintain a spacecraft in orbit. If you see, the velocity to maintain a spacecraft in the orbit is about 7.8 or 7.9 kilometer per second, unless the vehicle will not maintained in the some particular orbit while it is in operation. So these are what we have discussed last time: various type of propellant, cylindrical type, star type, and other various kind of. Okay, so different shape gives different propulsive mechanism or burning mechanism. Some of them are progressive burning. Okay, if it is simply cylinder, then progressive burning. If it is star type, we can get neutral burning. Okay, so in order to get neutral burning here also, in this case from outer and inner, there is propellant grain inside,